Okay, good morning, Assalamualaikum. So we'll begin from where we have left off. Let me just share the screen first before I forget. So we are still at lecture 6. Oops. Let me try to remember where we have actually left off. So I think we have come across, we have gone through this, right?
Yes. Yes, we
Okay.
have.
So I think we have come to the point of showing. Did I go through this? I just can't remember now.
Yeah, absolutely.
Okay. So the idea is in, you remember, let me just go back a little bit. We remember in the case of what you call the hydrogen atom, for example, we know that there is a n squared degeneracy that comes from the hydrogen atom states. Okay, so usually when we find degeneracy, we always think of no, there must be some underlying symmetry coming in. If there is no symmetry, then we call it as accidental degeneracy. But in this particular case, we do have some extra symmetry in the hydrogen atom through this idea of uh, Runge-Lens vector, okay, for which it is actually conserved in elliptical orbits. And we have shown that, okay, the Runge-Lens vector operator is actually behaves like a vector as it should. Okay, so it actually has this commutation relation between M and L uh, that has this, just like your angular momentum algebra. Okay, your epsilon ijk there. And then the only thing uh, that seems to be problematic is the fact that this M produces another operator here, which is essentially your Hamiltonian. Okay, so what can be done? So what can be done is that one can actually go to uh, con- the context of where you have the states being the eigenstates of the Hamiltonian. So one can actually fix this particular value, okay, to be the eigenvalue of the energy. Okay, and then we have actually mentioned that one can replace your, okay, there's a mistake here, uh, this vector M uh, by just rearranging the expression in terms of your energy, okay, to get the vector n, okay. And when you do this, then you'll find that, okay, the algebra for the vector operators L and N closes in this set of commutators. So in this particular case, one can say that, okay, since you have this closed algebra, then one should have some kind of a group that give rise to this particular set of closed algebra, and that group is essentially your SO4. Okay, so SO4 has 6 generators, and over here you have actually 6 operators, L1, L2, L3, and N1, N2, N3. And how can one actually see that this is an SO4 generators is by rewriting it in terms of your, for the L, for example, you write in terms of the cross product, and essentially you have this difference between the product of X's and P's, but the label goes from 1 to 3, and then the new one will goes from 1 to 4. That gives you your N1, N2, N3. Is this where we more or less stop, right? So in other words, what we have here, essentially all this what you call sort of antisymmetric combination of your X's and P's involve the components 1, 2, 3, 4. Okay, so in other words, that essentially tells us, okay, it's going to be some kind of rotation with 4 coordinates, your x1, x2, and x3, and x4, and the same thing for p1, p2, and p3, and p4. Okay. Now, the next thing that we want to do is essentially, despite that you have this kind of essentially closed algebra thing. So this is a closed algebra. One have a feeling that, oh, can one do better? Because over here what's going to happen is that you have your operators n, okay, sort of having the commutators expressed in terms of a different generator. Okay, so is it possible to rearrange your basis in the Hilbert space in such a way that one doesn't have this kind of thing? Okay, and in fact you can. The way is actually to redefine your operators, okay, in this sort of combination of L and N, okay, in this following way. So in other words, we have a sort of a symmetrized version of this, which gives you a vector operator I, and then the anti-symmetrized version of this will give you an the other vector operator K. Okay, and when you do this, you can recheck this. You should do the algebra properly. When you do this and you take the components of your I and K and take the commutators of them, you'll find that, okay, I have this components of I. When you do the commutator, will just closes on itself. Okay, so this is one algebra. In fact, this is an angular momentum algebra here. Okay, and then you do the same for your K, you get another set of angular momentum algebra here. Okay, so, and one final thing is we have to check in this particular case of the mixture between I and K, and you will find that, okay, in this particular case it seems like I and K is sort of committing with each other. In other words, they are in a way independent of each other. Okay, so that's interesting because one can now think of this just like one angular momentum here. So you can think of this like in the case of the spin, we call this as an SU2 algebra. Okay, and then this one will be another SU2 algebra. Okay, so I'm not sure whether I've introduced SU2 before. SU2 is just a double cover of your SO3 algebra. Okay. So in other words, okay, maybe before that. Okay. So the other thing that one should also have is the fact that you have this sort of square of your angular momenta here, given by I squared and also K squared. So in other words, from the theory of angular momenta algebra, these operators will have these eigenvalues. Okay, this is from your first course, and the eigenvalues of I and K is actually given by half integers or integers. Okay. If I don't have any other information about I and K, then your eigenvalues I, K here is going to be independent of each other, but they are not. Okay, they have another relation here, which is given by I squared minus K squared is given by L dot N, and L dot N is going to be equal to 0. Okay, so if we look previously in the case where you have the algebra L and the algebra N. Okay, so in that particular case, what happens is that your I must be equals to K. Okay. So that's interesting. No, in a way that this is just imposition in some sense by this what you call by this equation of operators. Okay, but in a way we do have this independence between this I and K. Okay? It's just saying that okay, you must have your I, your quantum number I must be quantum number K. Okay. Should again I've not edited this properly, but okay. So here is the difference between I squared and K squared. One can look at the other combination, which is I squared plus K squared, and that gives you this quantity, which can be expressed in terms of your L and M as before. And over there, if you remember, this is giving you I times I plus 1 h bar squared, and then this gives you K times K plus 1 h bar squared. Okay, these two things. But I equals to K, so that means that gives you 2K, K plus 1 h bar squared. Okay. And then one can actually combine this L squared and M squared. You remember earlier what is M? M is actually related to energy and this what you call charge. Okay, so you can actually get your right hand side over here in terms of these quantum numbers. Okay, and if one, so over here essentially you got your energy eigenvalues. So if you start rearranging this equation to get the expression for E, essentially what we have this expression which is similar to the case of the expression that we had solved when we solved the hydrogen atom Schrodinger equation, where instead of what you call in the previous case that we had was that this will be 1 over n squared. Okay, but now this is actually replaced by this 2k plus 1 squared. So in other words, if one substitute this, okay, essentially that gives the idea of this so-called degeneracy that initially we do not know where it comes from. Now we know it comes from the symmetry that which is in terms of the previous one is the SO4 symmetry. Okay? And this SO4 symmetry is not really what I call it, it's not explicit in the expression for the hydrogen atom, so it's sort of hidden within the expression of the Hamiltonian of hydrogen atom. Okay, so that was quite interesting in a way, because initially people was thinking in terms of accidental degeneracy, but now you know where it comes from. Okay, the other thing that essentially you see that if you do a kind of basis transformation, you find that your SO4 turns into a SU2 cross SU2, which comes into that algebra that we had earlier in terms of I and K. Okay, so why is this happening? In fact, it's essentially, if you do a little bit of group theory, okay, at the algebra level, SO4 is actually homomorphic to SU2 cross SU2. Okay, at the algebra level. At the group level, they are two different things. Okay, so this is essentially a very nice surprise that one gets from just studying symmetries of the physical system that one has. So generally, let me just conclude with this important remark that normally one actually looks at the continuous symmetries of the system in the Hamiltonian, and if there is some other symmetries, usually will be hidden, just like in this particular case. Okay, so and essentially one studies these symmetries in terms of Lie algebras, which is something that we have not actually properly introduced in this particular course or elsewhere, in fact, and also Lie groups. Okay, so this usually will require some more advanced course to show how the real definition of Lie algebras and Lie groups. Okay, so that is essentially where we have finished the last lecture. Okay, so let me go to the next lecture. We are continuing for today's. Again, I only just prepared this lecture notes this morning, so I was struggling to finish it up. Okay, and the thing that we want to discuss is essentially instead of continuous symmetry, we are going to discuss about discrete symmetries. And the first discrete symmetry that we're going to discuss is essentially what we call parity, or in more physically intuitive way is the space inversion. Okay, so what is a space inversion? So it's just like a reflection about the origin. Okay, so you have your R is actually transformed to minus R. So this is a transformation. Okay, and if you why is it discrete? You can see that if you do the transformation twice, you'll find that it gets back to the same thing. Okay, so this is the same thing as R previously. So sometimes people write this as a what we call a Z2 symmetry. And since you don't really, since the symmetry is discrete, okay, you don't really have any continuous parameter that sort of parameterize this kind of transformations. So one has to deal this a little bit more I'm in a way it's like an ad hoc operation, but one can actually justify this in a much bigger context. One probably need something like your Lorentz group, and which we'll come to that when if we ever get there, okay, in relativistic quantum mechanics. So how do we do this kind of transformation? Well, we just posit in this particular case, we know that any transformation is just like a change of basis. In this particular case, then you must realize it by a unitary operator. By the way, I have not uploaded this set of notes because I've yet to finish it. There's just one last section that I have not included into this particular lecture notes, so please bear with me. Okay, so this is essentially a unitary operator, okay, such that it will act on the space of states of the quantum states. So, for example, you have a quantum state alpha. It will transform to a different state alpha dash by acting on the state alpha here. Okay. So over there, you don't really see the idea of space inversion over there. Okay, you have to remember that the Hilbert space is not the real space, so it can depend on the space itself, meaning the configuration space where you have your XYZ thing, but the Hilbert space is just a space of quantum states. Okay, so one needs to make connections in a different sense, where you know that your position operators, for example, positions, okay, are represented as operators inside your quantum mechanics. So one would actually, okay, if one want to do this, then I will have to deal with the position operators. Okay, and how does one do this? Well, one can actually just think of an operator always get transformed by using the unitary transform, okay, directly, or one can have a much more physical intuitive way of doing this by stating that, okay, you know that in quantum mechanics, your average quantities are quite analogous to your classical quantities. So in other words, if you think this as a classical position, then that should be reflected inside your average values or the expectation values. So in this particular case, one would actually do this. So you have an expectation value of your position operator in the transform state, okay, and you want to simply replace your alpha dash here by the definition above, then you have this property, and as I said, the expectation value must follow closely with what is expected in terms of classical physics. This is sometimes called the correspondence rule. Okay. So you have in this particular case, this expectation value must be equals to this expectation value, just like you doing this kind of transformation. Okay. So in other words, in that particular case, you'll find that, okay, this operator pi, which is representing your parity operator. So initially I wanted to just leave out this hat. Then I started to think that, okay, it might be confused with the numerical pi. So I put back the hat inside this particular case. Okay, so so what can you say here? You can see that this must be equals to that. Okay, so in other words, the operator here, the transform operator, must be equals to the minus r. Okay, so this is what I mentioned earlier. So this is the transform. Okay, the transform will be related to the, in terms of the classical case given by this. Okay, and if you think what this is, if you just simply multiply pi, remember that this is unitary, so you multiply pi in this equation, then you actually get this particular equation. So in other words, here essentially is what we call an anti-commutator of your r and pi, which is r pi by r, because I'm going to use this later on. Okay, this is what we call anti-commutator. And this is called 0. Okay, right. So the other thing that one should be able to see is the fact that if for example, instead of this general state of alpha that one has over here, you replace this by the position eigenket. So replace it by position eigenket. Okay, in this case I'll just write the dash just to differentiate with this r without the dash. Okay, so over here then you'll see that, okay, what you're going to have your r dash r dash must be equals to minus r dash r dash. Okay, and then you see that, okay, this will amount to equals to r dash. Do I want to do this? Okay. Maybe not. Okay, I don't want to do this. But the idea is essentially one should be able to get this kind of your getting a bit. So okay, what I'm trying to say is this r dash is now an eigenstate of your position operator. Okay, so this is position eigenket. The question now is, what is pi r dash? Okay, now the reason that I do not want to go to that simple substitution over here, I should actually introduce more symbols, and then you have your direct delta function, which I do not want to go to that. So essentially we know that if r dash has eigenvalue r dash, okay, so this is the eigenvalue corresponding to this, then this one, because it goes under the space inversion, then it should have the eigenvalue minus r dash. Okay. So in other words, it's proportional to minus r dash. So being proportional, there is a constant of proportionality and we will actually normalize it right, then it's just a phase factor. Okay, so that is the essential claim over here. Okay, so you have a phase factor coming out by acting your parity operator onto the position eigencat. Okay, but what happens usually is it's just a convention. We'll take this phase factor here. Okay, the phase factor, we'll choose it as equals to 1. Okay, so in other words, this in fact this pi r dash again I made a mistake here. Pi r dash must be equals to minus r dash. So it's good that I have not uploaded this particular set of notes. Okay, so this is actually wrong. Right. Oh, this is not wrong. Sorry. What's that? This is not wrong because what I have here is actually pi squared. So this is okay. When you do the inversion twice, so essentially what happens is that I have pi minus r dash, okay, and then this gives you r dash. So this is, sorry about that. Right. So when you have this, so you essentially say that, okay, your pi squared equals to the identity operator. So that tells us the inverse of the operator itself is just the operator. Okay. So when you multiply pi twice, it's just like multiplying an inverse to itself, and you get this identity operator. But what would that say? Well, remember that we begin that your pi is a unitary operator. Okay, so that means pi dagger is must be equal to pi inverse, right? But now pi inverse equals to pi, so that tells us pi dagger equals to pi. And that is essentially saying that, okay, your parity operator is just a Hermitian operator. Okay, so that's quite nice. Being Hermitian, that means your eigenvalues of your operator has to be real. So the only way that this can actually work is in the sense that you get your eigenvalues must only be plus or minus 1. Otherwise, it could be a complex number here. But since it's Hermitian, then this eigenvalues is actually plus or minus 1. Okay, so the idea of the parity operator is to do space inversion. Okay, but now one has to see how this operator acts on other operators inside your physical system. So one of the important operator that one needs to find out how this parity transformation transforms the operator themselves is the case of the momentum operator. Now, if you really think of what it is in terms of classical mechanics, your momentum operator is just related to your what you call position operator by a time derivative. Okay? It's proportional to that. Okay. So in other words, if I do have r goes to minus r, then classically I would also expect p goes to minus p. But over here it gets a little bit complicated because here we are dealing, if one replace this by an operator, here we have a velocity operator that is not usually well defined. Okay, so we need to do this in a different context. And how do you do this? Is to use the fact that your momentum operator is the generator of your translation operator. I believe in the first course it should be introduced when we talk about the translation symmetry inside your, say, chronic penny model, for example. Okay, so but if you have not seen it, never mind. So the translation operator is just given by this. Okay, and how it acts on the wave function, it actually gives you wave function, say it's the argument is actually r here, and then this is translating about with the parameter dr, it becomes psi r minus dr. Now you might be confused, why is this minus instead of plus? Let me see if I can get my old notes over here. 3601, and if I can actually remember precisely which lecture it's supposed to be. Oh dear, let me see, 16, 20, maybe let me try 22 and see. Or maybe I just, what do I do? Lecture 22 is what? This is supposed to be in the first course. Probably lecture 23. Let's see. I'm not sure whether I still have these notes, the explanation for that. It's not here. Oh, never mind. I will try to draw the picture essentially over here. Let me see. It's like, so when you do, say, let's suppose I have a waveform here. So it starts at some kind of, what you call, at the origin. So what actually happens when I transform this in terms of this translation operator? Now, according to this, the argument gets translated to the left, right? So if I try to draw the same thing again, so let me draw this axis here, it gets translated to the left. So it will now start at this point, for example, and essentially, I'm not sure whether you can actually see this, but you can see as if this waveform have actually moved forward, and then it comes to this particular waveform. Can you understand that or not?
Repeat that.
All right. Essentially, on the argument, okay, on the argument is supposed to be sort of, let me see if I can do this a bit more properly. So you have when r equals 0 is supposed to be at the origin in the beginning, but now if I were to redraw the curve when r equals to the origin, it's actually giving you this minus dr. So it actually starts at this point. So in other words, hang on, that's why I need my old picture that I had drawn earlier in the old notes is better off than me trying to figure out. But essentially, what I'm trying to say somehow, let me think about it. And let's see, if I want to have the same picture with this translated thing, so got to think carefully now. Maybe it's not this picture. So this is R. Okay. It's actually this. So if you remember that, okay, this is psi r. Now, if I want to do the same for psi r minus dr, what's going to happen in this particular case, in order for me to get this this argument to be 0 again, I would need to be doing this. So this is actually your dr over here. So when you substitute dr into this argument here, so let r equals to dr, then your r minus dr will be equals to 0, and then you get back the same picture. Okay, so it's sort of counterintuitive. You're supposed to show that the waveform is actually moving forward, but the argument is actually moving in the opposite way. Okay, maybe you can figure out yourself. So in other words, this translation operator acts on the wave function in this particular manner. Okay. So under parity transformation, you can check that if you do this for this particular equation, then one needs this particular equation to be transformed in this manner under the parity transformation. Okay. So that is with respect to the translation operator. Now we can go back to our original question, is how does momentum operator change under the parity transformation. So what one can do is just simply use an infinitesimal version of this. And remember that this is generated by your momenta operator. So I can now make it infinitesimal. So I get your minus ip dot dr on h bar. So to first order, okay. And then this pi, I can put it as pi dagger on the other side. So I will have actually, oops, what did I do here? Let me check. I'm doing this in a rush, so that's why probably I get some mistakes here. No, there shouldn't be any pi here. Okay. So I get, because I already multiplied this pi daggers. So I multiplied pi dagger here, multiplied pi dagger here. So I get that. So you expand this, and then you get your operator pi, your parity operator, with your momenta operator, it anti-commutes. This is the one that I mentioned just now. I need this definition of pi anti-commutes with p. It means just simply equals to pi p plus p pi equals 0. Okay. And by rearranging this, then you'll be able to get what you need. Okay, so this is essentially no, it corresponds to what we have seen in the case of the position operator. Also, we also have the same thing for the case of the momentum. Okay. Now, okay, as I said, once you have a particular transformation, you have to see how how the other operators inside the physical system start to behave, because you cannot just have the transformation acting on a position operator alone without caring for the other operators. Okay? Because all the other the physical system as a whole will have other observables coming in, the other operators coming in, and then essentially you need to figure out what also happens to the others. So one of the things that's going to be important for us is actually the idea of angular momenta. Okay. So what would be the behavior of the angular momenta under parity transformation? Well, let's start with the orbital angular momentum, because that you know that angular momentum for the orbital angular momentum is just a rotational behavior in space, and you can actually express this operator as this cross product between these two operators. Okay, and again, I mean, this is just by ad hoc kind of assignment here in a way, but you can actually use your much more abstract way of doing this. But your L is just now your position operator cross product with the momentum operator. Okay, and since we know that, okay, under the parity transformation, for example, pi L pi, so this is supposed to be dagger here, that thing should be now pi dagger r cross p pi, and one can actually start doing this. Okay, so one just introduce an identity operator in between, which is given by pi times pi dagger, and then you get the thing you want. This is equals to minus r, and then this equals to minus p, and then you get back your r cross p. Okay, so in other words, we expect that in this particular case, your pi dagger L pi equals to L, or in other words, I can rearrange this equation. This will be equals to pi L equals to L pi, and I rearrange it again, then I get the commutator equals to 0. Okay, so this is good. Since this will tell us, okay, one of the things that we know is that when you have two commutators compatible with each other, then one observable, say, has an eigenstate. That eigenstate will also be the eigenstate of the other operator, which it commutes with. So in this case, your angular momentum, orbital angular momentum state, okay, excuse me, your orbital angular momentum state will also be an eigenstate of your parity operator. Okay, so that's great, but it will not actually address angular momentum in general, which includes spin. And the problem with spin, it doesn't have any what I call counterpart in a way to let's say in the case of orbital angular momentum, you know that it's actually doing rotation, but spin doesn't have those. Okay, so one needs a better way of deciding how this angular momentum behave. Okay, well, the one thing that we already know is that your general angular momentum is going to be what you call the generator of rotations. Can you excuse me for a while? Sorry, my cat wants to go out. Right. Again, one goes back to the classical case to give a kind of a hint what's supposed to be happening. So classically, for example, you have your 3x3 rotation matrices, okay? And under space inversion, you know that it's a matter of multiplying another 3x3 matrix to your rotation matrix. And that 3x3 matrix is given by this minus sign throughout the diagonal. So in other words, every coordinate sort of flips its value to the negative one. Okay, so your x goes to minus x, y goes to minus y, z goes to minus z. So in other words, in this particular case being diagonal, that means your rotation matrix will actually commute with your parity matrix here. Okay, so if one goes from this particular equation, how it should transform in the case of quantum mechanics, then you will say that, okay, I'm going to have my parity operator over here representing your parity transformation there, okay, and then your rotation matrix here is given by your rotation operator, and this must be commuting in the same way as this one is commuting. Okay, so if we do that, then it's now easy for us to see what happens in general. Then you'll find that in this particular case, if you remember, your dr is actually exponential minus I j dot n. N is some axis rotation, and then you have some rotation angle here. Okay. And if you do this in infinitesimally, then you get this particular operator, and then you plug this into this equation, and then you'll find that you can actually show that your parity operator pi commutes with the angular momentum operator J. Okay, in other words, you have pi dagger J pi equals to J, which is precisely what we have actually found for the case of your orbital angular momentum. But now it's now more general, and it also includes spin. If you, for example, write your total angular momentum as J equals to L plus S, that also amounts to saying that for your spin, then it must behave in this particular manner. Okay. Now, finally, we want to return back to the states itself. So again, if you want to see how parity transformation transform the states, what do you do? So a general state psi, for example, you can actually give a spatial dependence by taking the position representation. So I can take the position eigenket out dash inner product with psi, so that will actually give you the wave function. Okay. So in this particular case, under the parity transformation, then I will have something like this. And this gives you psi minus r dash And generally, your pi psi over here, so this psi minus r dash are usually not equals to, maybe not to say not equals, let me rewrite that, is not proportional at all to psi r. Okay, so in other words, in that particular case, no, you transform psi, which is generally a not, it's not an eigenstate of your parity operator, and when it gets transformed to psi minus r dash, okay, it also is not the parity eigenstate. But if for some reason that your psi is a parity eigenstate, then essentially you expect this to happen. Okay, so in other words, because it's an eigenstate now, so remember the eigenstate, when the operator acts on it, okay, will give you the eigenvalue. The eigenvalue here is plus or minus 1. Okay, so what if it is a parity eigenstate? Then it translates to the idea of your wave functions are now have a definite parity, which is saying that it's gonna, when it's parity plus 1, then basically you have an even function. When it's odd parity, then it actually corresponds to the odd. And there will be some physical system which are having those kind of what you call functions which have definite parities. So we're going to look at some of them over here. Right. So as I said earlier, your pi commutes with your orbital angular momentum. So in other words, your angular momentum eigenstate is also a parity eigenstate. Okay. So, and we have come across how to do eigenstates of angular momentum, particularly orbital angular momentum, for example. Then we just simply take your, usually we think of this NLM thing, okay, but here I can think of this can be any other quantum numbers here. So what we have in this particular case is essentially when you take the position representation of that state, of your angular momentum state, it will give you something with respect to the spherical harmonics. And there will be some extra thing correspond to this quantum number. Okay. So and essentially when you do the transformation from r dash to minus r dash, you know what actually happens to the what you call the angular coordinates for this particular transformation. Your r will stays the same, okay, because r is just your radial distance, but your theta goes to pi minus theta and phi goes to phi plus pi. So in this particular case, when you have your spherical harmonics, the important one here is actually your cos theta will go to minus cos theta, and your exponential I m phi will goes to minus 1 to the m exponential I m phi. Now, if again, I'm not going to go through this again. This is a spherical harmonics in terms of your associated I think it was Legendre, right? Polynomials. Okay. So this is the full what you call full form of your spherical harmonics where your associated Legendre polynomial is given by that, one can actually show that if you make these changes, then essentially your spherical harmonics will just change with this phase factor, which is given by -1 to the L. Okay, so in this particular case, for example, when you have L equals 0, which is your S shell, okay, then it's going to be positive parity, okay, because -1 to the 0 is 1. Okay. And then L equals to 1, which is your P shell, it's going to be negative parity, correspond to -1 to the 1, and then so on and so forth. L equals to 2 is what? D shell. Okay. So now essentially you have this confirmation in some sense, just a verification that your eigenstate of angular momentum is also an eigenstate of your parity. Okay. Now, as I said, this is not just for orbital angular momenta. Remember, your spin also is part of angular momenta, but without any kind of correspondence to a motion in space. Okay, so in this way, it becomes like, as I said previously in the first few lectures, your spin, your intrinsic quantum number spin is like a birthmark. So in other words, there will be some kind of birthmark with respect to this intrinsic angular momentum spin, which is also sort of comes together with the idea of parity birthmark. Okay, so in other words, if you look at the case of elementary particles, normally you also you are given what is the parity of the state of the elementary particles. An example is essentially your pion. I don't know if you know what pion is. Pion is essentially the messenger particles between say proton and neutron, for example. Okay, and that has a negative parity. Okay, and the ordinary matter particles, proton, neutron, and electron, by convention, is assigned to be parity +1. Okay, so once you have a standard assignment, then you actually can find out from the interactions of these particles with other particles, you can actually assign parity quantum number to the other particles. Okay, so this is actually done in particle physics. Now let's now suppose if we have the Hamiltonian also commutes with the parity operator. So in that particular case, just like in the case of your L phi 0 thing, here you have angular momentum eigenstate, then it must be also parity eigenstate. Similarly, if you have this to be happening for your Hamiltonian, then your energy eigenstate, okay, in this case this is your energy eigenstate, we call energy eigenvalue is En, then your N is also a parity eigenstate. Okay. So I'm not going to go through the proof, it's pretty obvious in this case. You can actually do the algebra. You can check that this one, for example, is actually a parity eigenstate. So you just multiply pi on both sides, and then you can actually get this equation which tells us that it's a parity eigenstate. Okay. So we can look at some easy cases. We have seen the case of the spherical harmonic. Another easy case that one can look at is essentially your harmony oscillator. Okay, so the harmony oscillator, if you actually see, you can see that you have this p squared and x squared. So in other words, you already know that okay, your p is actually anti-commutes, your x anti-commutes, but your p squared will commute with parity. Similarly for your x squared. So you can actually show this that your Hamiltonian then will be commuting with pi. So in other words, in this particular case, what do you expect in terms of your energy eigenstates of your oscillator, harmony oscillator? Then you expect them to be also a parity eigenstate. Okay. So in this particular case, for example, if you have actually seen a harmony oscillator eigenstate can be written in terms of what we call the number states. So these are the number states. So the number states, it begins with number 0, which is the ground state. And this ground state, if you have done harmonic oscillator properly, then you know that it has a position representation of a Gaussian wave function. Gaussian wave function is essentially symmetry. My drawing is not symmetric, but no, it's supposed to be symmetric. So then if it's symmetric, then it has even parity. Okay. And then if you try to go to the higher energy eigenstates, okay, then you just apply your creation operator here, okay, and your creation operator here is actually given by operators which are linear in x and p, and because of x and p are odd under parity transformation, then you expect this first excited state to be also odd under parity transformation. So in other words, first excited state is odd parity, and then you can go on if you want to the next excited state, say second excited state, this will be even parity, and so on and so forth. So generally what you get in this particular case, the states n will have parity minus 1 to the n. In the theorem above, there's one thing that we have actually forgotten to emphasize. This n has to be non-degenerate eigenstate. Okay, that means for each En, okay, there's only one state n. Okay, so there's no other state that correspond to the same energy. Okay. So, and for the case of harmony oscillator, that's the case, okay, or for that matter, for any one-dimensional quantum mechanical system, then you always have a kind of, well, I should be careful about that. Assuming no other particular symmetry, then you have a non-degenerate energy eigenstate. But when you go to more than one dimensions, when you have say 2 or 3 dimensions, an example is the case of a hydrogen atom, you already know that this has degeneracy. Okay, your eigenstate, which has En eigenvalue proportional to 1 over n squared, it has n squared full degeneracy. So in that particular case, you can see that okay, let's take this particular state, which is for n equals to 2, I can take L equals to 1 and L equals 0 state, okay, and then make linear combination of this. This state doesn't have a definite parity, because why? Here you have L equals to 1 is actually what is it? Minus 1 to the L, right? So L equals to 1 is actually odd parity, and L equals 0 is an even parity. So when you have a mixture between odd and even parity functions, then the whole state will not have definite parity. Okay? So the condition of non-degeneracy here is actually very crucial. Okay? So I'm beginning to get to the end of my notes. Maybe I will just go to the book later on. So here is some example of this particular case. Here is again one-dimensional quantum mechanics, which in a way I already mentioned that one-dimensional quantum mechanics without any other symmetries coming in, that's going to be having a non-degenerate and energy eigenstate. So here is a double well potential case. Okay, so you will have, for example, a state which is symmetric about this double well, and a state which is anti-symmetric about this double well. Okay, so in these two cases, you can actually see that, okay, this is going to be what? This is going to be if I actually have my what you call x equals axis over here, then this is going to be even and this is going to be odd. Okay. Then the other thing that you can also see over here is the fact that this has bigger curvature compared to this. Okay, this curves a little bit more compared to the even case, and then because of that curvature, you'll find that the energy of the antisymmetric state over here is actually greater than the energy of the symmetric state. Now, how do I know that? Well, your curvature is actually correspond to your del squared. Okay, your del squared in this particular case will give you a k squared. Okay, so this tells you about curvature. This tells you about kinetic energy. Okay. So in other words, greater curvature will give you greater kinetic energy. Okay, so let me go down here. So now what can actually happen? I can start making combinations of this symmetry and antisymmetric states. Okay, so your symmetry and antisymmetric states are going to be parity eigenstates. So in other words, over here, this one will not be a parity, not parity eigenstate. And let's suppose, so you do evolution of these states and see what happens. Suppose it at t equals 0 is in the R state. Okay. It's called an R state is essentially if you do this combination, what will happen? There are more probability going on the right side of the potential compared to the left side of the potential. So that's why it's called R and L, right and left. Okay. So if I begin with the R state, so there are more probability to be in the left side of the the right side of the potential. Then at later time t, you just use this time evolution operator. Okay, this will give you this. Okay, and you can actually rewrite this in terms of that. Okay. Now, why is this actually written in terms of this? Then you can actually see you have this oscillating behavior. This is just like a global phase. So the global phase doesn't actually, you can ignore it. Okay, and then this relative phase essentially tells you about the oscillatory motion. Okay, so the oscillatory motion is with respect to this particular case where if you go, let's define that your t equals to 2 pi h bar time divided by EA minus ES. Okay, then at half of t, you can actually work it out that this will it begins with a r t equals 0 state. Okay, then it goes to at t over 2, t equals to t over 2, it goes to the left state, and then it goes to r back when t equals to t. Okay, so what it does is sort of oscillates between the right state and the left state. Now remember that I mentioned earlier the idea of right state and left state is that, okay, for the right state, okay, for right state, the probability is more over here, and for the left state, the probability is actually more over here. Okay, so you can actually think of it, okay, it's like, no, okay, there are more probability over here. That means the probability to be to have the particle found in this part of the potential is more. So and for the left state, it's going to be over here. So you can think of it as tunneling through this barrier. Okay, so on and off this is going to be tunneling through, but in general it will be, no, there will be non-zero probability over here, non-zero probability over here. Okay, so the idea of this tunneling actually tells us, okay, you are able to get this kind of oscillation. Okay, with this frequency, this is sometimes called the Bohr frequency. And then what's going to happen if we do the following? Here it really depends on the barrier here. So the lower the barrier, the easier it is to actually tunnel through. Okay, the higher the barrier, then essentially the tunneling probability is going to be much less. So if you make the barrier to be infinite, then what's going to happen is that if it starts in this particular state, then it will get trapped in that state forever. Or if it starts in this particular state, will get trapped in this state forever. Okay. So in other words, what happens in this particular case, these two states are the corresponding, so S and A state. This S and A state in this particular case is actually degenerate. You can see why this actually happens, because if we take the probability squared of these two humps and dips, okay, they are just the same thing. Okay, so in other words, in this particular case, we have a degeneracy condition, and what's going to happen is that your physical state, okay, can be your right state or your left state, which is not a parity eigenstate. Okay, remember the condition that we had for the case of the energy eigenstate with a parity eigenstate. Okay, it has to be a non-degenerate condition. So in this particular case, it's not non-degenerate, it's degenerate. Okay. So in fact, this is actually an example of a broken symmetry. Okay, so when you go to the lowest state, for example, you either going to have this or this. So you have to pick one. Okay, it's like what you call in particle physics, it's like the spontaneous symmetry breaking kind of thing. Okay. So this only happens, of course, if your what you call your barrier is actually infinite, okay, in between. Now, why is this particular example being discussed is the fact that these are actually realized in certain physical systems like the ammonia molecule. you have these two different configuration that gives you the quantum states, and these are analogous to your right and left states that you have mentioned earlier. And then the other thing is in some molecules, for example, the chiral molecules, you actually see this thing happening again. So that's where my note finishes this morning. So there is a two little sections after that. Okay, so let me. Do you want to take a break now? Because probably not sure whether you're still there. Okay, you're still there. Do you want to take a break a little bit? And then we just have about.
Sure, doctor. Yes,
Okay.
please.
We only have a few more minutes. Okay, after that. Okay, let's take 5 minutes break. Okay, is everyone back? Okay, so let's continue, but I think we only have around 10 minutes, I suppose, because I don't have any more things to say at this stage. Okay, so for the next thing that we wanted to do, to give you this part. So these are the parts that which I have not actually prepared the notes. So the idea of a parity selection rule. So given say two states over here, alpha and beta, okay, as parity eigenstates. So parity eigenstates. Let's just write this as follows. Pi alpha is giving you a plus or minus here. Okay, so we do not need to determine what this is at this stage. And then pi beta is also having plus or minus here. Okay, so what's gonna happen is that if you have a kind of this is just like saying you have some kind of a process going on. So you have x operating on your alpha state, and then sandwiched with your beta state. What it actually says over here is that this quantity beta x alpha is going to be 0 if your alpha and beta is not the same. Sorry, I should not say that. I think the condition is here. Okay. Oh, it's actually the opposite. Sorry. Unless, sorry. Your epsilon alpha must be equals to minus epsilon beta. Why? Is essentially because your x over here has parity -1. Okay. So in other words, when you go, it's kind of a transition rule going from some state, let's say it's an even state here, because of the x operator acting on it, so it requires the what did I say just like even, right? Even, and then it becomes odd, and then this has to be also odd. Okay, so that's why you have this opposite parity must come into play. So the proof is actually given in this particular equation over here. So you just plug in your identity operator here. So you get pi inverse pi, and then pi inverse pi for the other side, and then you find that this actually gives you minus x. This gives you epsilon alpha, and then this gives you beta epsilon beta. Okay. So if they are the same, what's going to happen is that epsilon alpha and epsilon beta is both pluses or minus, then this will be equals to minus beta x alpha. Okay, or I can write this way, and that is going to be 0. Of course, that cannot happen. So in other words, the only way that this actually can work is is when epsilon alpha and epsilon beta is different. So in other words, their product will be -1, and then -1 times -1 here will give you back this quantity. Okay, so this is actually a transition rule that you may see later on in the more realistic calculations later on, so that it becomes what I call a rule that says that if you connect these two different states with this position operator in between, then if it's the same parity, then it will be just equal 0. Okay. In some other contexts, you might have not really the position. Well, I mean, it's related to position. In this case, will be a dipole moment, for example. Then we'll find that states which connect to itself, for example, will automatically becomes equals to 0. Okay, so these are things that actually can happen in realistic calculations, where parity actually tells you what is possible, what kind of transition is possible, and what kind of transition is not possible. Okay, so we probably will see this again when we discuss the Stark effect. Okay. Okay, one final thing before we finish is a kind of a mysterious thing that happens in nature. Initially, people thought that okay, a preferred state in nature would be symmetry with respect to parity, but apparently this is not, and this is only occurring for the case of the weak interactions. I'm not sure how much did you learn about weak interactions before? Have you come across weak interactions or heard about it?
Isn't that being responsible for radiation?
Yes, it's radioactivity. Okay, so weak interactions give you all these radioactivity processes, and these radioactivity processes are the only processes that which actually violates parity. So in other words, with these weak interactions, you can have parity violation. So that is essentially what this part of this section is supposed to be. Okay, I'm not going to tell you the details. You can read for yourself. The experimental discovery was actually given by I can't remember the full name, by Wu, it's a lady. Okay, and it actually shows that okay, there's a dependence on this parity through this quantity of S dot P. S dot P is actually it's actually it's like what, helicity kind of thing. I'm not sure. I've forgotten all the particle physics here, but essentially this is actually parity sensitive. Okay, and then they found that the parity actually changes under some of these decays that we have seen. Okay, so I think that's about it. So probably you can read this all by yourself, and then we'll continue with another discrete symmetry after this, which is going to be time reversal. Okay, so I will stop here today. So no, as I said, I have not finished up this particular set of notes yet. Any questions? You can start asking now. I will try to finish this. No, just after this lecture, and then I also have started to do your assignment. Okay. May I suggest your first test to be on the Monday of week 7? Is that okay? So it will be the Monday where we have this 2-hour period. So there you will have your first test.
Next week, doctor, or
This
the
is
following week?
this is
In 2
week
weeks,
5,
sir.
right? This is week 5, right? So next week will be week 6. So you have, at least you have a little bit of time to go through the assignment, okay, see the solutions, and then have a test on week 7. Okay. So I think that's all for today. You have any immediate questions that you want to ask?
Doctor, until what? The coverage is until what?
Most probably just until. Okay, that's a good question. Maybe at least it should include the addition of angular momentum. Whether I want to include tensor operators or not, okay, that no, it's difficult to find questions on those. Okay, so addition of angular momentum is the at least it comes to that. Okay, so let me take the attendance. Okay, so if there are no questions, I should end it now. Okay, thank you everyone. Thank you.